All right, real quick before the main video starts, I had two little typos and I don't feel like re-recording this a third time, so I'm just going to correct them once and then they'll show up wrong throughout the video, but you'll know that they should be the corrected versions. So first off, this X, of course, is just a Y, no big deal there. And then when we get to the polar discussion down here, my theta direction is kind of backwards. This, we could call that minus theta, which just really what that means is my positive theta direction should be out this way, and that's true on both graphs. So throughout the video, those two errors will show up here and there, but just know that what I just drew in are the corrected values for those couple of little things. Okay, this is largely in response to some questions asked about homework 3, question 6. I'm not going to go through that problem exactly, but I'm just going to talk a little bit more about frames of reference because that seems to be the issue, at least the questions that have been asked so far have revolved around. So what I'm going to look at here is just a random curve and a particle that's in motion along that curve at some point in space and time, and that's represented by the red dot here. And I've got a velocity vector on there on the left and an acceleration vector on the right. These have effectively just considered them known, for lack of a better word. We've seen lots of ways to calculate those, but right now, just those are the known magnitudes of velocity and acceleration. How they've been determined, we've seen that in different contexts, but for this case, just those are the magnitudes of velocity and acceleration. They're not specifically tangential. They're not x components, y components, radial components, anything of the sort. It's just that is the direction and magnitude, relatively speaking, of the velocity and the total acceleration at some point in space and time. And I'm just drawing it on separate curves for space concerns, essentially, just so that I can draw a little bit more detail around them. All right, so they're floating kind of on this curve. They've been calculated somehow, but to really refer to them or do anything with them, it's almost always required and necessary to put them in a frame of reference. And we've only talked about 3 ways of doing that. There are more, but the 3 we have cover the vast majority of cases, which would be Cartesian, normal tangential, and polar. So what I'm going to do is just take these known vector directions and magnitudes and show them in those 3 systems or 3 frames of reference. Because any of them can apply. A frame of reference is literally what it says. It's just a frame that you're using as a reference to quantify components of a vector. So if I look at, first off, the Cartesian system, right here, let's write that in. Normal XY plane. If I'm just kind of putting it in with the axes parallel to my screen. But what all you're doing is projecting that velocity or acceleration vector to those directions. So I define an x direction and I project my velocity vector into the x and into the y direction. That's it. Do that with typically kind of some little bit of trig, sines and cosines. If that function were given in xy, you'd be able to do these things pretty readily. But I could also put that x and y system in. I could show it anywhere and in any orientation I want to. If I make an x and y system way over here, I can still map that vector, not like that. I can still map that vector back to it. That's no problem. All that Cartesian system is, as stated, is a frame of reference, and you're just mapping your vector or vectors to that frame. And of course, same thing for acceleration. I can map that to an x and a y component. Here we've switched to a normal tangential system. The curve itself has not changed. The acceleration and the velocity vectors have not changed. All we're doing is changing the frame of reference. So I take And the normal tangential system specifies that the tangential component is parallel to the velocity vector. And that's because the velocity vector, and we've beat on this several times in class, velocity is always tangent to the path of travel. So your tangential direction in a normal tangential system is also parallel to your velocity, which means it is also tangent to the path of travel. Tangent vector, makes sense. And then your normal vector would be normal or perpendicular 90 degrees to that. And the only additional little bit of information there is your normal vector always points into the curvature. So my plot curves that away, my normal vector is going to point that way. That's always going to be the case. We looked at how you can calculate the radius of curvature if you need it for a sort of an XY plot at least. But the big thing here is just what we've already discussed, or that we discussed with the Cartesian system. You're just mapping your acceleration and velocity to this frame of reference. So for velocity, we know that we purposely put the tangential axis parallel to the velocity vector. And if two directions, or if a vector is parallel and you project it onto, or I'm sorry, if two vectors are parallel and you project one onto the other, its full magnitude projects onto it. So the tangential velocity is the full magnitude of velocity. It's just they equal each other. And then likewise, since the normal vector is perpendicular to the velocity, when you project a vector onto a perpendicular vector, you get 0. And there's just nothing there. So I mean, that's why we only have tangential velocity in a normal tangential system. So the full magnitude of velocity maps to the tangential direction. With the acceleration vector, we're going to have, or we can have, components in both the tangential and normal direction. That's okay. And that's why we say the tangential component is essentially v dot, because only the tangential component of acceleration influences the magnitude of velocity. And likewise, since acceleration is a vector, if tangential acceleration can only influence the magnitude of velocity, then the normal acceleration has to be the factor that influences the direction. That's just, it's a vector. If it's changing position or magnitude and direction, then if one thing is fully responsible for magnitude, the other thing has to be fully responsible for direction. But the overall process is exactly still what we talked about with the Cartesian system. You're mapping the red acceleration vector A into your frame of reference, and you're getting the two components. There's nothing special about that either. It's just the two components that are mapped into it. In the normal, if you were solving a problem with this, as you've done, you're typically or more often going to be solving for the tangential and normal components, which you can then use to find magnitude. But it's still just a vector mapped to a system. Once you find that magnitude of acceleration, you can map it to a new system. You can go right back to the Cartesian system and calculate it in that form. Or you can do the same thing with the polar system, which we'll talk about now. Now, the polar system, you're going to have an origin over here in this case, and you're going to have a radial vector that goes outward from that. Or I should say direction. You could consider it a vector, but we'll say direction or axis. That can move, but it can only rotate about the origin in this case. And then your theta direction is going to be perpendicular to your radial direction, as shown there. Once those are defined, and the origin of this system, I happen to have placed it more or less on top of the Cartesian system, so I can kind of compare them all, but it could be elsewhere. It doesn't have to be in the same spot. Typically there's something that makes sense in a problem to put it one place or another, but it could be anywhere. But once that is defined, your radial direction is going to pass through your point of motion. Your theta axis is going to be perpendicular to the radial vector through the point of motion. So those two are defined. And then same process. You've got your velocity vector, original velocity vector in red, and that maps to, projects to the radial axis and the transverse or theta axis as components. So if you can get the angle between the velocity vector and the theta and or r directions, you can just do that mapping directly. And likewise, same thing for the radial acceleration components. AR vector and a theta vector are just mapped components of the accelerations. And just like with normal tangential, in a problem, you're often solving for those, and then you can use those to get to the magnitude, but they can then be mapped again to any other system. So if I turn everything on, it's going to get super cluttered, but you can see I've got that red velocity vector is projected into 3 different frames of reference, but it never changes. Its direction does not change, and its magnitude does not change. It's represented as components in 3 different systems, but if I take the root sum square of any of those systems components, I'm going to get that original vector magnitude. And if I find the angle from any of those components, we did a little bit of that in class on Wednesday, that angle is going to be the same as well, because all I'm doing is referencing my velocity and my acceleration as well back to those 3 frames of reference. In problem 6, said I wasn't going to, but let's take a little bit of a look at that. You got something like that where it wants to know, you got something on this path. That should be a circular path. It's a little distorted there. And it wants to know basically, that's theta, that's r. That could be my theta direction. It wanted to know the accelerations about this bottom point in polar coordinates in the r theta direction. Well, on that path, I did exaggerate it a little bit here, but this is how it actually looks. The velocity vector, which is known and constant, it does not align to the theta or the r direction in this system. It's very difficult to solve for that immediately, but it does align to a radial theta system that looks something, well, it'd be more like this actually. Something like that. And that you could solve it. You can solve that problem with no issues whatsoever. It also would sit very nicely in a normal tangential system that looks like this. Normal, and then your tangent is out here. Just like that. So you could take either one of those 2 systems, the red or the blue, solve for your acceleration, then that vector in the direction you solve it for, that is your acceleration, and all you have to do is map it back to this frame of reference. That's how you solve this problem. That's how you solve a lot of very unique and kind of interesting problems in dynamics.